Now we are in example 3 in disasters MCM. I'm going to run this in MATLAB. You can run it in OpenBox, but it runs a little bit longer. We are talking here about maybe 100 seconds running in Octave as opposed to a few seconds in MATLAB. If you run this in Octave, you will need to download actually the load package statistics, because we are going to do run sample because of the full conditional on M. But for MATLAB, this run sample is part of the distribution, so we can comment out this for MATLAB. The next one in this example is the program, the description of the data that I was mentioning, and some references concerning this data set. Now, this is the data set. X's are essentially the numbers of disasters, coal mining disasters, for the years listed in the dataset year. So the years go from 1851, that year would be year 1, up to 1962, that year would be 112. And let's see how the program works. N is the length of the dataset. We are going to take 10,000 simulations of MC with 500 burn. Lambda is going to be at the beginning zeros. Mu are going to be zeros, and M are going to be zeros at the beginning. And we are going to get start points. M1, the very first one is 10. And then we are going to simulate from the posteriors and add this one. Lambda 1 is going to be 4, and mu 1 is going to be 1/2. This indices 1, 1, and 1 correspond to the index in MCMC run, the very first one. It is the starting point. Then we set the hyperparameters for our priors. For prior on lambda, we have alpha 4 and beta 1/2. For prior on mu, gamma delta, it's 1, 1. Let me see alpha beta for 1. And gamma delta, gamma was 1/2 and 1. Although the setting the hyperparameters is important, if the data are such that they are overwhelming the prior, it may not be so relevant. But we'll see it could be relevant because it is important to be close to the whatever number of the accidents was observed, the rate of the accidents. Okay, so we set the parameters, hyperparameters for the priors, and then we measure with this tick and tack time needed. We start from second observation, second simulation to the last one, and then we form these two quantities alpha 1 by summation of x's up to mm, and beta 1 mm plus beta. These are needed for lambda. So we are simulating lambda now, random number, with parameters alpha 1, and be careful here, we need to take not the rate as second parameter, but the scale. So it is 1 over beta. 1, 1 means a single observation. The same thing for gamma and delta, and we simulate new mu as gamma distributed with gamma 1 and 1 over delta 1 because of the scale, single observation. And then we have also posterior of mj, which is proportional to this expression that I was talking about, and then we find this for all n years. And at the end, we sample random number between 1 and n, single one, with repetition, but not in this. This is not important in this case because we have single number, with posterior Rm as the weight. So essentially, we sample from 1 to n with random sample with weight distribution corresponding to this posterior for the m. And here we have only posterior, which is up to the constant. Random sample takes care about normalizing this to have probability 1. This works for all n simulations. Then we take into account burning first 500 observations, and then we plot the histogram of m, which is the posterior for the change point, for lambda and mu. So let me run this. So here we go. The first figure here is the posterior distribution histogram. Actually, this is discrete distribution over the years for m. And we see that actually the 1891 has the highest probability posterior probability to be this change point here. Posterior distributions for lambda and mu are given in this expression here. Take a look for lambda. The mean is about maybe a little bit bigger than 3. And mu, the mean is below 1. So these are rates of accidents before and after the change point, the posterior distributions. So that concludes the 3 examples and this unit on the Markov chain Monte Carlo.